In this video, I'll be introducing the topic of mechatronics and robotics. The learning outcomes of today's session includes the following. In this video, we will be examining what we mean by mechatronics and then go on to look at the various types of robot that are being used today. Following this, we will examine what controller options we have for our mechatronics system in terms of the computing hardware and what language would be suitable to use to program our system. In today's final video, we will explore the various mechanical engineering aspects related to our system. In particular, you will gain an understanding of what structural components are needed and the associated calculations for this. We will consider transmission systems that allow us to transmit the torque to the required locations. And we will conclude on how to transform these engineering designs into the required technical drawings.
So mechatronics. So I've taken this from Bolton, the book. So mechatronics, integration of mechanical, electrical and electronic control engineering and computer technology in the design, manufacture and maintenance of engineering products and processes. So the point about mechatronics is you're not looking at sort of three different disciplines in so much as you do something mechanical, you do something electrical and you do some computing and stick it all together. The point of mechatronics is sort of a synergy of doing the whole design from the outset. So you have to consider the electrical and mechanical parts together, how the programming is going to sort of interface all this together. So when you come to mechatronics engineering, you've got to think of the whole system from the outset. So this is a schematic of a mechatronic system. So we'll start with the microcontroller. So this is either a microcontroller or computer, and this is sort of the brains of the system. This will power some kind of actuators, so these might be motors or pumps. And in order to achieve this, it'll have to go through some power electronics. So the controller decides what it wants to control, that signal gets amplified and then powers your actuators. The result of them actuators will get sensed, so we have some sensors in here, and then these feed back into your microcontroller, so they either feed back in directly or we need some kind of signal conditioning electronics to be able to do that job. So that is your basic mechatronic system. All this needs some power management. So in terms of sort of your voltages, current going in. So we need some power management in there, and then we need some user interface so you'll be able to interact with this system. So a lot of these topics we've covered in instrumentation and drives. So we've looked at Arduino programming, so we've kind of done the microcontroller part. We've looked at a LabVIEW interface, so we've done the user interface part. We've done motors in instrumentation and drives, so we've done to some extent some actuator technology and the H bridges to drive these, so we've kind of covered this as well. And we've looked at some sensors. So in terms of the mechatronic system, we've actually covered quite a lot of this already in the instrumentation and drives module, and that is the point of the instrumentation and drives module. It's a kind of introduction to mechatronics engineering. So we will need all these aspects for our mechatronics, but in terms of this module, we'll focus mainly in this aspect, the power management and the signal conditioning part. So that'll be our main focus in developing our mechatronic systems. But bear in mind, all of these components are needed for a mechatronic system. So we will be using all these, but you have got quite a bit of prior knowledge to a lot of these from the other module. So there's a range of mechatronic systems we can use as a sort of a demo system for the module. So most systems or most appliances in your house are essentially mechatronic systems. So if you think about all these, for example, a DVD recorder, digital camera, laser printer, they all have some mechanical aspects to them. They all have some electrical aspects, and then they've all got some kind of intelligence, so there's some controller in there. controlling all the operations. So all these are mechatronic systems. Even a washing machine is a fairly intelligent machine in terms of measuring the load, knowing what temperature, measuring how sort of dry it is on the spin cycle. So there's lots of systems we can use as a demo example. What we do in this module is look at robots. So it is a robotics module, and it's also a mechatronic system. So we'll focus on building our mechatronic system around building a robot. So I believe it's a bit more interesting rather than, for example, discussing about a washing machine. So in that sense, a bit more exciting to do. But bear in mind, all these systems and a lot more are all mechatronic systems. So if you can build a robot, then it's sort of a small step to all these other systems. Just slightly different specifications, but essentially the same technology: mechanical engineering, electrical engineering, and computing in there. So, in terms of robots, what we'll be looking at, we'll keep it relatively simple, and we looked at wheeled locomotion. Okay. So there's advantages of just looking at wheeled robots, which we'll come on to. But I just want you to bear in mind there's lots of other options. We can have walking robots, UAVs, so for example drones. You can even get robotic fish. So there's lots of options for robotic systems. So as I said, we'll be just doing the wheeled version, but bear in mind there's a lot of others out there. Apart from the kinematic model, so in terms of driving the wheel speeds, then that's applicable to wheeled robots. But everything else we do, path planning, sensors, etc., it's applicable to all types of robots. So it's got far wider application than just the wheeled ones we'll be looking at. Okay, so if you mention the word robotics, what do you think of? Well, this is probably the first image that comes to mind is something like this. So this is essentially the state of the art in the world today. This is a spin-out company from MIT called Boston Dynamics. If we just go onto their website, these are the kind of robots they develop. So we'll just have a quick sample video. So we'll call up Atlas. This is an exceptional level of sort of technology and programming expertise. So our course won't be quite this in depth, but in terms of state of the art, this is what you're looking at. So there's lots more examples on the Boston Dynamics website. So I suggest you have a look at that to inspire you into robotics. Now, a lot of you might be thinking, it's good to watch, but I'm not going to be actually doing that kind of engineering when I leave university, which would be a fair comment. However, I don't want you to think of this as the only type of robots out there. So, for example, let's have a look at some household robots. So these are commercially available systems. You've got a vacuum cleaner. So Roomba was the first one to do this. A robotic vacuum cleaner. There's lots more examples out there now. Robotic lawnmowers, another case of what's available. And then you can go and buy these products. And as an engineer, you might actually, if you go out and sort of work in an engineering company, you might start developing products such as this. So there is a fair chance you'll actually be doing some kind of robotics engineering in the future. We've also got sort of cars. So a lot of cars today, or the push is to try and make cars self-driving. So this is Google car, lots more examples, BMW, etc. But again, these are just robots essentially, autonomous robots. You're going around doing a job, getting from A to B. It's just you're sitting as a passenger inside. Okay, so if you're enjoying this module and think, oh, I like robotics, but I probably won't be doing it, there is probably a fair chance you might have some aspect of robotics in your engineering job, as all today's engineering becomes sort of more intelligent systems. Okay, so in terms of robot stability, we saw that Atlas robot there balancing. So if you have to balance, it's quite a difficult control task. It's nice if a robot is stable to start with, it makes things a lot easier. So if you have at least 3 points of contact, so if I can get this pen to work again. Right, so one there, and one. So if you have 3 points of contact and you draw a line between these, if your center of gravity for this falls somewhere in there, then the robot is stable. Okay, so if you stop it, and then you don't expect it to fall over. If you have less than 3 points of contact, so for example, the Atlas robot had 2 feet. Okay, you're not forming a triangle there. You've got a straight line. So the center of mass is never going to be exactly on that line. So the chances are it's going to fall over. If it doesn't fall over, then it's known as dynamically stable. Okay, so you can get a robot always to be stable, but if it has to do some kind of actuation to maintain that stability, that's dynamically stable. Our ideal case is we want it to be statically stable, so have at least 3 points of contact with the ground, put your center of gravity within that contact area, and then you know if you switch the robot off, it's not going to fall over. In terms of robot geometries, we'll be looking at wheeled robots. It makes things a little bit simpler in a lot of respects. The advantage, well, the main reason of using wheeled robots is robots tend to be used in man-made environments. So we tend to use them in areas we have specifically designed. So with that, I mean the area is structured, so we know kind of where things are at. Surfaces are usually smooth and well defined. Okay, so because robots are used in these man-made environments, we have these advantages here. We know what the environment's like. And the advantage of a wheeled robot, or for example that walking robot that we saw at Atlas, construction is a lot simpler, so they're very easy to make. They're a lot more efficient. Something moving on wheels takes a lot less energy than something having to walk. And also in terms of modelling it and controlling it, it's a lot easier in terms of a wheeled case to, for example, a walking robot. So we'll keep this module just looking at wheeled robots. It's the predominant type of robots out there, and they are the easiest ones to understand. Given we're using a wheeled type of robot, we've got the options of different wheels. We've got our standard wheel here, so that's just a normal wheel you would find in most places on a car, etc. So that's our standard wheel. We've got caster wheels. So you might find these on, for example, shopping trolleys. So it's a wheel that can move in any direction. Caster wheel is free rolling, so you kind of drive a caster wheel. It's only there for support. A standard wheel, you can drive it or let it freewheel. An omnidirectional wheel is a special kind of wheel where you've got the main rolling like a normal wheel, but you've got these extra rollers on the side here, and these allow the wheel to move sideways. So there's advantages to that we'll see. So these can be free, so freewheeling, or we can use them as drive wheels. I've just put a gamma equals 0. I'll come back to that in tomorrow's lecture. So you can just ignore that for now, but that is just defining the wheel geometry. And then Mecanum is a driven wheel, and it's essentially an omnidirectional wheel. So it's essentially the same as omnidirectional, except the casters or the side rollers at 45 degrees. So these rollers are at 45 degrees, and that gives you some kind of advantages as well. So we've got these 4 different types of wheels we can use in our robot. and then that sort of lends itself to what is the geometry of the robot. So what we'll do is just look at some typical geometries of how we'd build a robot up to get us started. So the simplest kind is called sort of the differential drive robot. And here you've got two drive wheels. So these are your standard wheels. So here's this is a student project, and the student built a robot consisting of two drive wheels. Now we said we need, for static stability, we need at least 3 points of contact. So we've got here essentially a free wheel to sort of roll and just support the robot. This can be a caster, or in this case it's an omnidirectional wheel. So we're not driving this, we're just using this as support, and this is free to roll either in that direction or, well, backwards or forwards or left or right. So that just gives us some stability. The two wheels on the side are your driven wheels, and this is what's sort of making the robot go in different directions. In this case, we've also got another omnidirectional wheel at the back, and again, this is just to give us extra support in the robot. So we've got 4 points of contact. So as long as the center of mass is within this, the robot is stable. It's also useful, if you see in this design, is that you have got your drive wheels sort of symmetrically placed. So the center of mass and the center of sort of the geometry is in the center of this line of action of the drive wheels. So that kind of makes things like when it comes to the kinematics a bit simpler, in so much as, you know, when the robot turns, it's always going to be within this radius. Okay, so it's just something to bear in mind. We'll come on to more examples of this as we go through the course. But if you can keep your robot geometry simple and sort of symmetric, it makes other problems a lot easier. So the differential drive robot is your most common type of robot. The other common type is what's called the omnidirectional. These are typically 3 wheels. They can be 4. They can be as many as you want. But they're normally 3-wheeled. And you have an omnidirectional wheel there, and there. Now, in this case, these wheels are used as drive wheels. So, for example, if I drive that wheel at that speed there, and that wheel at that speed there, I don't drive this one at all, but this one is just free to move in them directions. You'll see the robot will go in that direction. If, on the other hand, I drive this wheel, so if I drive this wheel and let this one free run, then I can get it to go in that direction. So I can get the robot to go in any direction depending on which wheels I drive. So in that case, it's very maneuverable, the robot. 3 wheels is a typical one. As I said, you can use 4 wheels for this. So 3 wheels is typical. Once you get more than 3, so 4, 5, 6, you need some suspension on the robot to make sure all wheels are in contact with the ground at the same time. Okay, so that's what makes the 3-wheeled robot a bit of a simpler scenario, is you always have all the wheels in contact with the ground. Once you have 4 more wheels, then if the ground is slightly uneven, one of the wheels might not be touching the ground. Hence the importance of suspension. So there were your 2 main types. Other types, this is Ackermann steering. An Ackermann is essentially what you have in a car. So you have some kind of drive at the back. So these wheels are your drive wheels. And then the front wheels are steerable. So you can steer these in different directions. So these are not maneuverable in so much as your omnidirectional. So you're a bit more limited in terms of how you can move the robot left, right, forwards and backwards, etc. So you do get less maneuverability, but what that does lead to is better sort of traction to the road. So for example, you can go around a bend a lot quicker on an Ackermann steered type of system than you can on an omnidirectional type of system, which will tend to slide sideways. Okay, so there's benefits and trade-offs for the type of geometry you use. But this would be your typical geometry for a car, for example. The Mecanum is an interesting one. The Mecanum is a four-wheel drive system, but what you have is a wheel. So this is your wheel here. And the wheel gets driven forward, but because you've got rollers on the side, you don't actually get a pure force going forward. What you can do is resolve that force into two components, which are sort of perpendicular to the rollers and parallel to them. Now you're not going to get any motion parallel to the roller. It's only allowed to roll in this direction. So the roller will only roll in this direction. So you won't get any motion due to that component. You'll only get motion due to this component. If we resolve that back, then that means you're getting a component of force in this direction and a component of force in that direction from the wheel. So the wheel is giving you the option of driving it forwards or sideways. So depending on how you drive each wheel, you can get different motions from this robot. So if I just get a video up of that to demonstrate. So that's your typical forwards, backwards and turning. So that's what you'd expect from a normal wheel. But then when you drive them in a particular way, you can actually get the thing to move sideways as well. Okay, so the wheel type does give you a lot of flexibility in the maneuvering ability. So in terms of maneuverability, is defined as how many degrees of freedom the robot can instantly access. So we're talking about robots being on a flat plane, so a robot can move in the X direction, it can move in the Y direction, or it can rotate about the Z axis. Okay, so we've got 3 degrees of freedom for a robot that operates on a flat surface. So if we think about the different robots we had, the differential drive, we could drive that forwards and backwards, that's the X degree of freedom. So for the differential drive, we can either go forwards and backwards, so that's X. We can potentially rotate with that. So that is our theta. So that's 2 degrees of freedom, but it cannot go sideways. So the robot cannot sort of slide in the Y direction. So that only has 2 degrees of freedom. The omnidirectional, depending on how we drive the wheels, we can get it to move in X direction, Y, and rotate. So that has got all 3 degrees of freedom. The Ackermann, so our typical car, can move forwards and backwards. So it's got X. It can turn, so it has got theta as well. Turning is a bit slightly different in this case because it doesn't turn instantly. It can only turn when you point the wheels and then move forward. So the turning of the Ackermann is actually linked with the X, the forwards and backwards motion. But again, 2 degrees of freedom. And then as you saw, the Mecanum can go forwards and backwards, sideways, and turn on the spot. So that has got 3. So when you come to design your robot, you want to think about how much maneuverability you want out of that robot and how you want to be able to access the environment. So there's some options of, there's your typical wheel geometries for a robot. I don't want you to think you're limited by that. There's an infinite possibilities just in terms of wheeled alone, let alone walking, swimming, etc. So there's plenty of examples out there. Here's a couple of examples. So this one here is your typical Explorer robot. So this is the Mars Explorer from NASA. So it's got a 6-wheel configuration, and the point of that is it's to have good sort of stability over very rough ground. So it's got a sort of especially mechanical design to help it overcome this rough terrain. Here's an example of what's called BallBot. This is a one-wheeled robot, so this will be unstable, or to make it stable, it'll have to be dynamically stable, so you need sensors on there to help it balance. But as you can see, it's got one drive wheel, which is essentially a ball to allow it to go in any direction. So there's lots of options when you come to design a robot. I don't want you to feel limited by just the examples I've given you there. You can design any configuration you want. So the aim is to design the robot to be able to do the job you want it to do. Okay, so that is just a brief introduction to the module and mechatronics, what we'll be aiming to do, and sort of get you thinking about some of the types of robots we might be looking at. So in the next video, what we'll look at is the computer hardware used in these robots and the options for what software we might use to program them.